project, you will understand a little bit better what it's about. Okay, so going back to our distillation column, we've defined at least three factors in this case, which are potentially important factors in the process. So the condenser temperature is given as one, the reflux rate, and the reboil temperature. So going back to our distillation, so we have a reboiler, a condenser, and then the reflux rate, so the amount of distillate that we send back into the column. So these are the three factors which we are considering here, and we're doing a factorial experiment with two levels. And so we call the levels -1 and +1 for each of the factors. So this is -1 being the low level, +1 the high level, or whatever the values are. So they're not given here. But just understand -1 is the low level, +1 is the high level. And so what we can then do is organize a full factorial experiment, which means that we look at all possible combinations of the factors, the low and the high level. So minus, 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 so this run 1 would be low for A, low for B, low for C, A, B, and C being our three factors. Okay? So these are the three knobs that we can tweak for the process. And so we've kind of said, okay, for us, the range for these factors is this. And so we'll go low side of the range, high side of the range for each of these three factors. And we do all possible combinations of that. And that gives us 2 to the power 3, which is 8 possibilities. And so we can then run tests. And so what you see here is a graphical representation where this corner would be the which run? What do you think this corner is? And we have 8 experiments, so 8 corners. So this would be -1, -1, -1. So this would be the first run. Okay, so this run. And so the 8 would be here. Okay, so all of the factors at their high level. And all the other combinations are given, and so we have 2 replicates, of which the average would be this, and that seems to be correct. Yeah. Okay, so 2 replicates means that we do each of these runs twice. And typically we do that in a randomized order. Okay, so we have 16 experiments we will do. Okay, and then we randomize the order in which we'll do these experiments, because all of us are very lazy, of course, so that's the nature of humankind. So our default would be that, okay, we'll do run 1 first. Okay, that's the measurement. Yes, of course. What are we? The response variable, I didn't even say it. This is the concentration of acetone in the product. So we need a response variable as well. So we're measuring something. And so we're looking at, in this case, the concentration of acetone in the product, and we want to have this at the highest possible value, for instance. Okay? So this is the idea of the experiment. To find the conditions which maximize this concentration. So, yes. What was I talking about? This is interesting. So we have 3 factors, 1 response variable, and so we're doing 16 experiments in a randomized fashion. We measure for each of these experiments what the response variable value is, and that we can then graphically put in such a cube format. Okay? So obviously this is just designing the experiment and then performing the experiment. We do the actual measurements in a random fashion because we don't want to have some bias. Okay, we turn the knobs in a certain position, then we do the experiment. We want to have the full variability of the system. So if we do the same condition, the same run again, and we do 2 replicates, we want to turn the knobs again, right? Because the turning of the knobs, getting the position exactly right, is of course also has also some aspect of variability. Okay, also implicates some variability. So we want to do this in a random order. There may be things like temperature of the environment, which is going in a certain direction. Okay, maybe increasing or decreasing. So we want to get rid of any bias which would lead us to wrong conclusions. So we randomize. This is important also for your experiments. When you do the project, you randomize the order of the experiments. Okay, but it's part of the tips in the project. But please take care of this, because otherwise you can get very strange results. Okay, so why we do this type of design of experiments? Because 99 out of 100 times, when people do this type of experiment for their master engineering thesis or PhD thesis, they go at a totally different. They do it totally differently. What is an actual way of doing this? I ask you to optimize a process, and you have 3 variables. What do you do? What does everybody do actually?
The minimum and maximum. You try the minimum, you choose one of them, and you try the maximum individually.
Yeah. So you start with one of the factors, and you say, okay, for instance, I'll look at temperature, and then you see, okay, for this temperature, this is maximum. Then you go and look at the next one, which may be the concentration of some reagent, and then you maximize that one for that temperature. Okay, and that is making a huge assumption. It's making the assumption that there's no interaction between these factors. So the interaction between factors, and this is shown here. So what is the interaction actually? It shows that the concentration of this acetone is a function, obviously, of the reflux rate. Yeah. But this effect of the reflux rate, if you go from low to high reflux rate, is dependent on the actual temperature. So one of the other factors. Okay? So the increase in concentration at the low temperature, if you go from reflex rate low to high, is not so large, but if you do it at the other temperature, it is very large. So there is this interaction between reflux rate and temperature. And if you do a one-at-a-time approach, which is the classical approach that people take, you do not catch this. And that's a shame, because you're missing an opportunity here to actually maximize this concentration. Because you're treating the problem too simplified. And then you may say, but this one-at-a-time scheme, it's much less time, it's much more frugal. No, it's not. So with the same number of experiments, you can actually get also this interaction information out of it. So there's no excuse to do a one-at-a-time experiment. Okay. So every time I see a masterpiece with a one at a time experimental approach, you have to have a fantastic excuse. Yoga, you want to make an excuse.
I would ask something.
Okay.
If we do all the combinations anyway, even if we do it one at a time, if we do all the combinations, it should cover it.
Yeah, but one at a time experiment doesn't do combinations. It fixes all the factors except one, and then varies that factor. And so you only see the response. It's like you have an equation. Okay, so if we have our response variable being x, okay, and the three factors A, B, and C. All right, so if we do a one at a time, we basically only look at variations in A, so we can only look at this coefficient in front of this A variable. Okay. So what I'm saying is actually we also need to look at things which are AB. So where we have in the modeling of the response variable, we also have terms which contain products of the factors. So you need to have all the combinations, A, B, and C, in twos plus A, B, C. And so what the statistical method allows you to do is to determine the size of these, all these coefficients, and then you can see if it's important or not important. Okay? And maybe this AB is not important, but here we see it is important. So these two, obviously, there is something going on with temperature and reflux rate. Yeah? Yeah.
ABC, but you need a 7 that way. And last time you said you needed to relate experiments for 8 vectors.
Okay. We're doing at least 8 experiments. And with these 8 experiments, you're right, we have 7 of those, plus we have a constant here. Okay? So whatever this constant is, I'll call it K for constant. Yeah, okay. Okay. So we also need to look at that one. That was very smart. Okay. So, but I'll try to convince you again of this later, but I want you to have a grasp of why we're doing this right now. Of course, we'll look at this in detail later. But I want you to have a grasp of this so that you know what to do for your project. So you'll do a design of experiments. But when you're thinking about which project, which experiment you would do, it's good to understand what the terms are. So there's factors, there's response variables, there's replicants. Okay, and typically people want to do a lot of replicates, 5, 6. Don't do 5 or 6 replicates, because this is against frugality. We don't want to do 5 or 6. We want to do maybe 2 replicates. That would be fun. Okay. So don't spend a week doing this experiment because you want to do 100 experiments. This is not the point. We want to learn as much as we can with doing a limited number of experiments. Okay. And of course you can up this and make a 4-factor factorial experiments and 5, 6, 7, 8, 9, and 10. Of course, it goes as 2 to the power of the number of factors, the number of experiments, for a full factorial. So there are techniques to bring down the number of experiments, and this is called fractional factorial experiment. And these fractional experiments, for instance, if you have 8 or 10 factors, this becomes essential to use fractional, because otherwise you just get lost in the number of experiments. Okay, so this is important to understand. And you should also understand that this type of full or fractional factorial 2 to the power k experiment is like a screening experiment. Okay, so it's screening to allow you to see which factors are the most influential, the most important factors. And then secondly, you can do the actual optimization with, so I'm talking about a complicated system, right? So you have a lot of factors, so you want to first see which are the important factors, which are the not so important factors. So maybe you start with 8, in the end you see there's 2 or 3 factors which are the dominant factors for the installation or the experiment that you're conducting. Okay, with these 2 or 3 factors, you then do an optimization. You go and look for the optimum, and this is a method which we'll see at the very end of the course, and this is what is called response surface method. So it's basically a method which allows you to walk on the surface which is defined by your factors of interest, important factors, and the response variable. And so by doing a walk, steepest gradient walk, you then find the optimum. So in that case, you're not doing this type of factorial design, but you're doing a response surface method, looking on this response surface to where the maximum or the minimum is, depending on what the question is. So that's also part of your project, and since last year I'm putting a lot of emphasis on this last part as well, because I want you to see the double approach that we have. First, screening experiment. Secondly, we go for the actual optimum. Because with the screening experiment, you can actually get some type of model. So you'll get this model, but it's not, if the question is important enough, you want to really model it well and get the optimum. And with this mathematical description, you may get somewhere, but you may not get close enough. So we want you to also learn about this response surface method. Okay, so that's where actually I wanted to be.